Hello everyone, welcome to Deep Codes, and in today's video we will discuss LeetCode question 2528 that says maximize the minimum power city. So here you are given a zero index integer array stations where stations of I represent the power of that station, and further you are given one range R. Okay, and and the range R is then a power of a city I can provide power to all cities from the range of R, that is in the previous all the before R cities and all the after R cities, where the modulus of the distance is less than or equal to R. So let's say for this city 4, it can provide all R cities before and all R cities after also, because we are taking here the absolute difference. Okay, um, so this is the absolute difference, and further the power of the city is the total number of power station it is being provided power from. Okay, so for a city I, it can get power from all the cities in the range of R. So sum of all this power is equal to power of the city, right? Now further the government has decided to give K more power station to city I. Um, so further we are given to we need to find maximum possible minimum power of a city. So we need to maximize the minimum power of a city by using K more power station. Okay, so I hope you got the question. So let me just try to brief you out once again. Here we are given a station array where station of I represent the power of city itself. Further, a city I can gain a power from all its neighboring cities in a range of R. And further, we need to maximize the minimum power by adding K more power station to any of these cities. Okay, got it. So now here in this first example 12450, we have R equal to and K equal to 2. Let us now try to understand this. So here we are given station equal to 1 2 4 5 0. So this is the power of a city itself. Further, a city I can gain a power from all its neighboring cities in a range of R, and in the end we can add 2 more power stations. Okay, let us now calculate the initial power. So initial power, so this city, let me give them indexes 0 1 2 3 4. So this city 0 can gain a power from this city 1, because the difference of 1 minus 0 is less than equal to R, but not from city 2 because it's not in the range. So for city 0 the range is till here. Okay, so if total power for city 0 is 1 plus its neighboring in the range, that is 2, so it is 1 plus 2, that is 3. For city 1 it can gain power from city 0 as well as power from city 2. So its power is 2 plus 1 plus 4, that is 7. Similarly for city 2 it can gain power from city 1 as well as city 3. So its total power is 5 plus 4 9 plus 2 11. Similarly city 3 can gain power from city 2 as well as city 4. So it's 5 plus 4 plus 0, it's 9. And city 4 can gain power from city 3. There is no another city right side, so its only total power is 5. Now here the minimum power is 3. Okay, now we have to use 2 more power station to maximize this value. Okay, so let's say one way is you select the minimum of all the power and add to it. So the minimum here is 3, so I add 1 here, so it becomes 4. Then this will become 8 11 9 5. Okay, now for the 4 is minimum, I can add one more k, that is 5, then it will become 8. This will also become 12 in that case, because this power increased. Okay, then here it will become 9, this will be 11, this will be 9, this will be 5. Okay, so here the minimum power is 5. Okay, so it is our answer. So this is one way to do this question by selecting the minimum power at each stages, but this is a wrong way, and it won't give optimum result in all the cases. So this is wrong. Now let us take another example where we will prove that this solution is wrong. Okay, now let us try to take another example to understand this. So let me take it station 5 station, that is 1 2 0 1 2. Let me take R equal to 1 and K equal to 2. So now let's first calculate initial power equals to, so let me number them 0 1 2 3 4. So this CT0, as the range is 1, it can gain the power from adjacent CT, that is CT1. So total power for this CT0 is 3 1 plus 2. For CT1 it can gain power from CT0 as well as CT2. So total power here is 3. This CT2 can gain power from CT1 as well as CT3. So its power is 3, 2 plus 1. So here this CT3 can gain power from 2 as well as CT4. So its total power is 3. And similarly here total power is 3. Okay. So now as per the above intuition or above approach, what we were doing is we were selecting CT with minimum power and we were adding 1 to it. So let's take here, let's say here we add 1. So now the power would be 4 here. Now so adjacent CT power would also increase, it will become 4, then 3 3 3. So still 1 K is remaining at this position. K is equal to 1. Here it was 2, so we added 1. Now K equal to 1. We again take the minimum CT with minimum power and add 1 to it. Now the power would be 4 4 4 4 and 3. Sorry, here it would be 5 as it gained power from here as well. So this would be the final power and our answer would be 3. But do you think this is an efficient approach to solve this question by selecting the CT with minimum power? No, because we can gain answer better than 3, and let me show you that how. So here instead of what we so here the power was, let's say at this stage it was 3 3 3 3 3. So instead of selecting let's say here this is our first CT where we got where that is minimum power, but instead of adding 1 here, what we would do, we would add the rightmost CT from which it can gain power. So for this CT, the rightmost CT where this CT can gain power is this one. So we would add here 1. Okay. So now the final power after this operation would be, this will gain power from so here it will be 4. This will also be 4. This will also be 4. And here 3 and here 3. Okay. So now the next possible minimum what we can say, the minimum power station is this. So instead of adding plus 1 here, we would add the maximum rightmost distance from which it is gaining power. So it is this node, this station. So we would add 1 here. So after that our answer is 4 4 4 4 and 4. So here as you can see we have gained a better answer, that is 4. Which means this is a maximum possible minimum power station. So this is better than this answer. So instead of doing instead of selecting the CT with minimum nodes and adding to it, what we would do is we would take the CT with minimum power and add power to the rightmost CT of it. So it can also get means it can be beneficial for CT furthering that CT. So I hope you got the solution or got the intuition of what we would be doing is one approach is what you can do at every stage. Means you can take min heap. At every stage you can increase the power of I plus rth CT. Then you will calculate power of each then you will again calculate power. So this would be, let's say this min heap take n log n time, and to calculate power at after each time of increment this would again take n time. So this would be the time complexity of this solution, n log n into n. Okay. Now but another approach you can do is to do with binary search. Okay. So with binary search, why binary search? Because whenever you think that there is something like sorting here needed, let's say because we need the minimum of this minimum power station, and then we will check the value that yeah if it is possible or not. So what we so at that point you can think of a binary search, because also the constraints are 10 raised to 5, so you can't do n square approach. You have to do something with n log of n into n, something like this. So this is one also approach, but binary search would be easy to code. So we will look for binary search. So this is one way of our thinking of binary search at this type of problem. So how you will do binary search? You will do binary search on answer. That is, you will take a range from L equal to 0 to high, that would be sum of all the station plus k, and you will iterate between these two. So you will take a while loop between these two and select a mid. So if it is possible to gain power of each station by taking mid, means it's if it is possible such that power of each station would be at least mid, that is power of I should be at least greater than equal to mid after k operation, then yeah, mid is one possible answer. So that means mid is one possible answer. So because mid is minimum possible power of each station, right? And in this condition, what we would do, we would go to the right hand side, or we would just make low is equal to mid plus 1. Why? Because we need the maximum of minimum possible power. So this is how we would do this, or do binary search. So in the helper function, we would do the same way. We would if any station has less power, then we will take the rightmost station from that and add power to it. Okay, so I hope you got the intuition of how we will solve this question. So now let's move on to the coding part. So we will be most of the operation would be done in long. So let me first define LL as long, so it's better to code and more readable. Let me first calculate sum of all the stations. So for ST of stations, I would simply add to the sum. Now I will take the low as 0, high as sum plus k, that is the maximum possible answer, and let me take answer as int min, because we need to maximize the answer. So now let me write the standard binary search while loop. Let us take the mid as low plus high minus low by 2, and if it is possible to that every station has minimum of mid power in the and by passing this R and K, then what we would do, we'd simply update our answer as maximum of answer comma mid, and we would increment low equal to mid plus 1 to find better answer, and in that condition we would simply decrement high to mid minus 1, and in the end we would return answer. So now our task is to write or code this possible function. So it would be a boolean function, stations vector int st ll mid int r int k. Okay, now let me take one current variable, current as equal to 0. So this will store power, current power. Let me take another vector additional of size n comma 0. So additional power to station I. So if we are using k or increment adding the any power with the help of this k station, so we will store in this add. Before that, let me initialize n as station dot size. Okay. Now firstly we would calculate for the station 0, right, and store it in the current. So this is what we will be doing. This is like a sliding window technique. So let me just code and under tell you by coding. So I equal to 0, I is less than r, I plus plus, current plus equal to station of I. Now I will start from 0, I is less than and I plus plus. So let me go to the here and let me tell you how we would be doing this. So let's say we have the station 1, 2, 5, 3, 4, any such station like this, and we need to calculate this power of station 1. If let's say r equals to 2, okay, so the power of station 1 would be 1, 2, 3, 4. Sorry, the power of station 0 would be station 0 plus station 1 plus station 2. Okay, so that is 5 plus 2 plus 1, 8. So first, and for station 1 the power is station 0 plus station 1 plus station 2 plus station 3. So that is, we have pre-calculated this, that this is 8, and we just need to add another power. So that is 8 plus 3, 11. Now for station 2, what we would do, we have for station 2, its power would be power of station 0, then station 1, then station 2, then station 3, then station 4. Okay, now since we have pre-calculated this, we would simply add the power of station 4, that is 4, so it would be 15. Now for station 3, so this is similar to prefix sum, okay, or sliding window. So initially the window was still here, so for this number the window increase, for this number the window increase up till here. Now for this number the window will decrease till here. So because we can't include station 0, that is out of this range of 2, so we would include station of 1 plus station of 2 plus station of 3 plus station of 4. So that is 15 minus station of 0. Okay, so that's 14. So this is how we are calculating the power. So instead of looping, we would do it in big of n time instead of n square. Sorry, not n square, n into r. Instead of n into r, we would do it n by taking the prefix sum in the current variable. So this is this logic we are applying here. So for this station 0, we calculate up till r minus 1, so it's less than r. So now if I plus r is less than n, then we can add to current with station of I plus r. And also we will add some additional power station if we have added in the add. Now if the current is less than mid, so in this situation we need to add some of the k stations. So I will take one need, that is needed power equal to mid minus current. So if need is greater than k, so we cannot fulfill it, so we will simply return false. This is not possible. In the and if it is less than or equal to k, then we would simply do is make k minus equal to need, current equals to mid. So because we have added needed station, so now it becomes equal to mid. This is the minimum power we need. We reduce k and yeah, and what we do, we added I plus r equals to need, not I plus r. What we would do is minimum of n minus 1 comma I plus r. So adding power to rightmost station. Okay, so this logic we have already discussed. And yeah, if I minus r is greater than equal to 0, then what we would do, we would simply decrement current. Let's say for the station 3 we have to minus subtract this from the current power, subtract the power of station 0. So this is simply we are doing here I minus r and current minus equal to addition of I minus r. Okay, so this is a simple logic, and in the end we would return true. So this is the only condition that will fail. Now let me try to run this. Okay, pass all the test cases. Now let me try to submit this. Okay, so our code got submitted. So the thing to note here is we need to add power to the rightmost station. So if you don't do this, then whatever would be your logic, it would fail in some of the test cases. So I hope you guys understood the question as well as approach and how to build the intuition to solve this type of problem. If you have any doubts, do let me know in the comment section. Do subscribe this channel and also like the video if you understood the question. Thank you.